So hey guys, welcome to ProtonsTalk. The topic of today's video is sets, and this is the part 2 of the topic. If you want to watch the part 1, you can find the link to that video in the iCards in the description below. I highly recommend you to watch part 1 first and then only part 2 so that you can understand all the concepts pretty well. So in this video, we are going to cover Venn diagrams and set operations. So firstly, let's see Venn diagrams, okay? So Venn diagrams was given by an English mathematician called John Venn, after which this name's Venn diagrams come, okay. Venn diagrams are basically a diagrammatical method of representing sets, okay. We use rectangles and closed curves, which are usually circles, okay. People can use other curves other than circles as well, right? So here we use rectangles to represent the universal set, okay. If you don't know what is universal set, I highly recommend you watching the part 1, right? And circles are used to represent subsets, okay. This is a bit confusing. Let's see with it. Let's see it with an example. Then it will be clear, okay. Now let's take two sets, namely A and B. Let's say A have 1, 2, 3 and B have 3, 4, 5, okay. Now as we know, universal set will have 1, 2, 3, 4, 5. Let's take some more elements, 6, 7, 8, so that I can show you everything in Venn diagrams, okay. If these are the three sets and universal set, then we have Venn diagrams something like that, okay. We take a rectangle which represents the universal set, and then we represent A and B with circles actually. Now if you say this is A, we can see that A is 1, 2 and 3, but B also have 3, so it have a common element, so these will be intersecting actually, right? So and usually people write the elements in here, so this will have 1, 2 and the common element is 3, and B will have 4, 5, okay. And the universal set also have 6, 7, 8, so this will be written here. So as mentioned, universal set is represented using rectangles, and the subsets are represented using circles, okay, right. There are you can draw these in different ways, right? Because here 3 was common, these were intersecting. If there is no common element, these won't be intersecting, okay. These will be like something like this. These will be disjoint, okay. And if if A is a subset of B, then this will be something like this, okay. B will be here and A will be inside it. So there are a lot of things, you know, depending on the sets for which we are drawing Venn diagrams, these will be changing, right? Let's see set operations. There we will also see Venn diagrams to understand those operations, and that will make this also clear, right? So let's move to set operations here. And the first set operation, as most of you might be knowing, is union. So let's see the definition first and we'll understand the example. So definition is just for formality, right? It's generally confusing. So it says that the union of two sets A and B is a set C, which consists of all those elements which are either in A or in B, including those which are in both, okay. So let's take example and understand it. Definitions are always confusing. So example, it says let's take A, which have 1, 2, 3, 4, and let's take B, which have 2, 4, 6, 8, 10. Okay, now union, which is represented by this U shape. So if A union B we want, it's A union B. So this is the symbol for union operation, okay. So A union B here will be, now it says that elements either in A or in B or both of it, right? So 1 is there in A, so we take 1. Now 2 is there in A as well and 2 is there in B as well, okay. But we should take only one instance of it, right? So 2, and then 3 is here, 3 is here, so we take 3. 4 is in both the sets, so we take only one instance. Then there is 6, so we have 6, then we have 8, and then we have 10. So this is how you build a union of two sets, okay. So A union B is basically this. If there is one element in both the sets, then you take only one instance. If you have only in one thing, then you just get it here into union set, okay. I hope you that is clear, right? It's not that difficult, it's just simple. Okay, that was a union. Let's see some properties of the union which are really important. Now the first property is commutative law actually. Let's try to understand these laws using Venn diagrams so that you get clear with Venn diagrams as well. So if we take first diagram, A union B is equal to B union A, which is the commutative law. First, let me show what is a union in a Venn diagram. Okay, so let's suppose that these are intersecting sets. They have common elements as well. And what will be the union of AB? Union will be everything, right? All the elements in it and the intersecting elements as well, right? So A union will be this, and obviously B union A also will be this, right? It will be this only. So those are equal, right? You got it, right? Then let's move on to the next law. Let's not waste more time on that. So it's called associative law, which says that A union B union C is equal to A union B union C. Let's take three sets here, okay, because we have three sets in an associative law. So if you take one set here, and one set here, all of the three are intersecting. So what it says is A union B union C, okay. So it says that let's say this is A, this is B, and this is C. So A union B will be this one, okay, and union C will be this one. If we come the other way also, B union C will be this one, and if you union A also, it will be this one. So these are equal, right? I hope you're understanding it. If you're not, just comment down below so that we can make it easy and more detailed from next time, okay? That way we improve and you also get more good content to see, right? So it's a win-win. Let's see third law. It says that A union null is equal to A. Now this is simple, right? If A is 1, 2, 3 and null, as we know, it's empty set, as I mentioned in the part 1. So obviously A union null is A only, 1, 2, 3 only, because there are no elements in null, right? So it's A union null is null, obviously. So I hope you understood that. Fourth one is A union A is equal to A again. Now if you take A is equal to 1, 2, 3 again, and A is again 1, 2, 3. So it's union of A and A. So 1 is here and 1 is here. So union will be 1, and 2 is here, 2 is here, so 2, 3 is here, 3 is here, so 3. One instance only, right, as we discussed. So that is fourth law, fourth property. A union A is equal to A, and A union phi is equal to A. We have names for all these laws actually. I'm not focusing more on the names. And then we have last property of union here, which is universal set. Union A is equal to union. Universal set, right? So A is 1, 2, 3, and if we say universal set is 1, 2, 3, 4, then obviously A is a subset of universal set, as we know. Every set is a subset of universal set, and 1 is there in both the places. So we take one instance of 1, one instance of 2, 3, and 4 is here in universal set, so it's 4 here. So we got universal set again, right? So that proves that universal set union A is again universal set, right? So those were the laws or properties of union, and that was union basically. It's not that difficult. It's just taking elements from either A or B or both, right? That's it. So let's move to the next operation, and it's called intersection, which is denoted by this kind of U, the reverse U actually. Okay, the definition says that intersection of sets A and B is a set of all elements which are common to both A and B. So this is basically the common elements, right? So let's say let's take an example again. A have 1, 2, 3, 4, and B have 2, 4, 6, 8. Now A intersection B. So as I mentioned, intersection is a symbol here for the operator here, operator symbol. will be the common elements. So 1 is only here in A, it's not there in B, so 1 is not will not be there in intersection, and 2 is here in A and B as well, so we'll take it here. 3 is here in A but it's not there in B, so we won't take this. Then 4, it's here in A and it's there in B as well, so we'll take 4. And A is, that's it, it doesn't have any other elements, so obviously 6 and 8 won't be there in intersection because these are not there in A, right? So that will be the intersection. If you want to find it using Venn diagrams, so let's say this is A and this is B, and obviously intersection will be 2, 4 here. So this area, which is the intersection area, is basically A intersection B, right? And as we mentioned before, this whole area will be A union B, right? And this small set which I have darkened is A intersection B, right? Okay, so that is A intersection B in Venn diagrams. So intersection will also obviously have some properties as in union, so let's see that, right? So the first law is again commutative law, which says that A intersection B is B intersection A. Now that is again obvious, right? We take two sets, then if this is A and this is B, then A intersection B will be this area only, and B intersection A also will be this only. So all the elements in this area will be in A intersection B also and in B intersection A also. So both of these are equal, obviously. Right, so that was first law, commutative law. Then there is second law, which is associative law, wherein we have 3 sets. Okay, so it says that A intersection B intersection C is A intersection B intersection C. So if we take 3 sets, A, B and C, and we have A intersection B, which will be this one, right? And for this one we have intersection C, which will be this small area here, right, which is intersecting with C. And then if we have A intersection B intersection C, so B intersection C will be that small area and this one, and then intersecting with A again will be this small area, right? Let me change the color here. So this small area, the intersection of 3 will be A intersection B intersection C. So this will be A intersection B intersection C as well, and A intersection B intersection C as well. So both of these are same, right? We just saw, right? So that proves the second law. It does not prove. We are just seeing examples so that you understand the laws. Okay, so the third law is law of null and law of universal set. It says that null intersection A is null. Now that is obvious because A, if it is 1, 2, 3, and null as we know is empty set. So there is nothing to be common, right? There is nothing in empty set to be common with A. So obviously the intersection also will be nothing. It's empty, right? And the second part of that law is universal set intersection A is A. Now we know that if we take a Venn diagram, this is universal set and this is A. It's inside the universal set. So intersection will obviously be A, right? If you want an example as well, if U is 1, 2, 3, 4 and A is 1, 2, 3, then 1, 2, 3 and 1, 2, 3 are common. So A is common in U, right? So intersection will be obviously A. I hope you're understanding that. As mentioned, if you don't understand, just comment down below. We'll try to improve. The fourth law is the idempotent law, which says that A intersection A is A. Okay, that is obviously obvious, common sensey thing. If A is equal to 1, 2, 3 and A is again obviously 1, 2, 3. So in A and A will be common, right? A is 1, 2, 3, A is 1, 2, 3. What is common? A is common. So obviously then A intersection A will be A, and that is called idempotent law. Then there is distributive law, which have both intersection and union. It says that A intersection B union C will be equal to A intersection B union A intersection C. Now let's try to see it with a small Venn diagram here. I'm sorry, I'm making it congested. Let's try to be as clear as possible. Okay, so let's say this is A, this is B, and this is C. So what it says is A intersection B union C, right? So B union C will be this area, and A intersection of it will be, let me take another pen. So A intersection of that will be this area, right? Right, you're getting that, right? If we take a Venn diagram again, I'm running out of space, but okay, that's why I'm trying to erase it. Okay, so that is erased. And if we take the right hand side, it says A intersection B, which will be this part, right? And A intersection C, which will be this part. So it's again the same part. I hope you're getting it right. It's again the same part we're selecting. So A intersection B union C, the part we got is again the A intersection B union A intersection C part as well. So that shows the law is correct, distributive law, and it's called intersection distributes over union. Okay, so those were the properties of intersection. I hope it's clear. So let's move to the third set operation, which is the difference, and it's denoted by minus only, as the name suggests. So what it says is the difference of the sets A and set B in this order is a set of elements which belong to A but not to B. So here important is order. Actually here order is important. Here A minus B is not equal to B minus A. Okay, now let's take an example and understand. So if A is equal to 1, 2, 3, 4 and B is equal to 3, 4, 5, 6, then A minus B, okay, A minus B will be removing the B elements from A, which will be 1, 2. So 3 and 4 are there in B also. So these elements won't be there in A minus B. Okay, and B minus A will be B elements, removing the elements which are common with A. So that will be 5, 6, as you can see. Let's understand this with a Venn diagram. Actually, that makes it really clear. So if you take here A and B, and that have an intersection here, AB, then here A minus B part is this one, leaving the intersection, and B minus A is this one, leaving the intersection again. Okay, so that is how you find. If you write the elements, you will just get it from here. Whatever elements lie in this area will be A minus B, and whatever lies in this area will be B minus A. Okay, so this is B minus A, and this is A minus B. Right, so that was the third operation. Again, it's a simple one, simple operation, minus or difference. Okay, I hope you understood that. And the fourth operation, the last one, is called a complement of a set, which is generally denoted by the small bar here. Okay, so complement of A is A bar or A dash. Okay, so let's see what the definition has to say. It says that let U be the universal set and A a subset of U. Obviously by definition A will be a subset of U, so U is a universal set here. Then it says that the complement of A is the set of all elements of U which are not the elements of A. Okay, so symbolically we write A dash to denote the complement of A with respect to U. Okay, so A dash is the complement of A with respect to U. Okay, let's understand this with an example if you haven't understood. Okay, so let's take U, which is 1, 2, 3, 4, 5, 6, 7, and A, let's take as 1, 2, 3, 4. Okay, so the universal set and A are there. So the definition says that all the elements of U which are not the elements of A. So 1, 2, 3, 4 are elements of A. but 5, 6, 7 are not the elements of A, so 5, 6, 7 will be the complement of A. So A dash will be 5, 6, 7. Okay, if you want to understand this using Venn diagram, so if this is U, then this will be A because it's a subset, and 5, 6, 7 will be here, and 1, 2, 3, 4 will be here. So all this area, excluding the area of A, whatever elements fall in this area will be the A dash, and this will be the A. Okay, right, so that is it. That is a complement. There are some properties, important properties of complement, which we have to see. Okay, so the complement laws are there. These are two complement laws. Let's see what are these. Okay, so the first law says that A union A dash will be universal set, and the second part of it says that A intersection A dash will be a null set. How? Let's see that. So this is A, and we know that this one is A dash, and we know the whole thing is U. Right, so obviously this is A dash and this is A, so A plus A dash or A union A dash will be universal set, right? So that's obvious because this part and this part is universal set, obviously, right? So intersection, we know that these are not intersecting. There are no elements in common. Okay, so you can see clearly that this is not common. There is no common area between A and A dash, right? So intersection obviously will be 0. It will be a null set, right? There are no elements which are common in A and A dash. So that shows this one, right? And if you didn't understand this, we can take an example. So A let it be 1, 2, 3, and universal set let it be 1, 2, 3, 4. So A dash will be obviously 4, right? So 1, 2, 3 is A, and 4 is not there in A, so A dash will be 4. So what will be the union of A union A and A dash? It will be 1, 2, 3, which is there in A, and we'll have 4 as well, which is there in A dash, right? So that is A union A dash, and this is universal set, obviously, which you can see here, right? So that was the first law. Then coming to the second one, you have De Morgan's law, which is really important. A union B complement is equal to A complement intersection B complement, and A intersection B complement will be equal to A complement union B complement. Let's try to understand this with a Venn diagram actually. So if you have an intersecting set like this is A and this is B. Now listen carefully because this is important law and the proof is also not that simple because there are two things here. So it says that A union B complement. So this thing is A union B, and the whole thing again, the unshaded part is A union B complement, right? So this area is A union B complement. Now that was the left hand side, right? It says that is this outer area is equal to A complement intersection B complement. Okay, let's see that. Let me just erase this. It says that we have to find A complement first. So A complement is this one. Hold the B part as well. And B complement is this part. Okay, without A. Now if we want to find the intersection, now as we saw that in B, A complement B part is not there, and in B complement A part is not there. So if we intersect, we just get this area, removing A and B, which is obvious, which is also A union B complement. Okay, I hope you understood that. That's a bit difficult there. Just listen to it carefully once again and you will get it, right? So that was De Morgan's law. Just remember the law. If you're not understanding the proof for this Venn diagram thing, it's not a big problem at this point of time, I guess. So there is another thing, a complement of complement is equal to a. Now we can prove this with an example. So if a is 1 comma 2 comma 3 and u is universal set is 1 2 3 and 4, then a complement will be equal to 4. We already saw this example, right? So what will be a complement's complement? So a complement is 4 and it's 4 is there in this. So to find a complement's complement, we have to get the elements of elements of universal set which are not there in a complement. So 4 is there in a complement, 1 2 3 are not there in a complement, so a complement's complement will be 1 2 3. Okay, and what is it? It is a again, right? So that was law of double complement actually. And the last law here is law of empty set and universal set. It says that empty set's complement will be universal set and universal set complement will be empty set. So that is obvious, right? Empty set is null set and universal set have a lot of elements 1 2 3 4. Now by definition empty set doesn't have anything, so we need not remove anything from the universal set to get empty set's complement, and thus empty set's complement is universal set. And the second one, to prove it, we need universal set's complement, but by definition we need to remove the elements from universal set whosever complement we want to find, and because here we want to find universal set's complement only, we'll end up removing all the elements, and thus we get null set. So universal set's complement will be null set, right? You'll probably have to listen to it more than one times to understand it properly. And that's it guys. I hope you got to learn about sets from this video, and I also recommend you to watch the part 1 so that you understand all the things clearly and you will excel in sets. If you have any doubts or anything or any suggestions for improvement, just put it in comments so that we can work on it from the next video. That's it for it guys. Do like, comment and share and subscribe to the channel. Thank you.